Hello friends and welcome to this video. We are learning wavelet transformation in the subject Advanced Digital Signal Processing, and to see the overall development of the wavelet transform as a mathematical tool to address the various signal processing applications. We have a study of Haar wavelet theoretical point of view. So from previous few of the selected videos, we are having a focus on the Haar scaling function, and then we shall be having the understanding of the Haar wavelet function. So as in the previous video where we have defined a functional space capital V0, thereupon we have tried to have representation of any type of a signal with the help of this capital V0, but we have seen a condition that thereupon for the specific unit time intervals there should be a constant amplitude level, then and then only we can have capital V0 as a functional space used thereupon. So it created a need of more finer Haar scaling functions. That is why the current topic here we have titled the same, finer Haar scaling functions. So let us begin to see what are the details and how we can find more finer Haar scaling functions and how do we get benefited by making more finer versions of the Haar scaling function. So let us begin with the topic. So here we can start with our topic, the topic titled finer Haar scaling functions here. So in the previous video, what we have seen as the various translated versions of the Haar scaling function. So Haar scaling function in original was denoted by phi of t here. Now to make more finer Haar scaling function, for the original Haar scaling function, it was the amplitude level 1 for the time interval 0 to 1. So if we try to have a reduction into the time interval, let us for example make it to first of all half. So instead of having the constant amplitude level equal to 1 for the time duration 0 to 1, let us make it 0 to 0.5 here. So in the original case of phi of t, this was the span here. Now if we make it to only 0 to 0.5 here, so the time what it was phi of t only, if we write it phi of 2t, it is actually the scaling to this particular time interval, but it is a reduction into the time interval to make it half here. So here we have the span 0 to 0.5. So for the original scaling function, here we have defined for 0 to 1, we are making two parts, 0 to 0.5 that can be denoted by phi of 2t, and then from 0.5 onwards up to 1 that we can denote by phi of 2t minus 1. So in this regard, we can get the finer Haar scalings from the earlier what we have said to be the translated versions to be the basis of the functional space capital V0 here. So for every element thereupon, we have two sub elements here. So here we have phi of 2t minus 2 and phi of 2t minus 3 in the place of phi of t minus 1. Phi of t minus 1 was spanning for the amplitude level 1 for t is equal to 1 to 2. So here we have two parts. Here it is the first part of it and here it is the second part of it. So I hope you are getting my point that we are reducing the time interval for the functional basis here and forming a new basis set here. So this new basis set in general will be of the type phi of 2t plus 1, phi of 2t, phi of 2t minus 1, phi of 2t minus 2, and so on. So the general representation we can make it to have phi of 2t minus k here. Here I have shown phi of 2t minus k here. So as we are forming the new set of the basis functions, I will be calling these to be the basis functions or the basis sets only when these are satisfying the criteria of the orthogonality and that of the orthonormality here. So in simple words, I can say that if they are non-overlapping with each other, so that time we can check the orthogonality to be satisfied among these new functional basis set elements here. So as we see here, there it is no overlapping. We have the distinctness from 0 to 0 0.5, 0 0.5 onwards up to 1, 1 to 1.5, 1.5 to 2. So all this I have shown in the positive side of the time axis t. On the negative side also we can go for, and yes, there it is non overlapping, and we come to see the orthogonality can be validated here. So let us be calling this particular functional space a new one, which is more finer in the resolution as compared to the earlier that we have defined in the previous video here. So this will be the set of the functions phi of 2t minus k in general, where k is belonging to the set of integers that we can denote it by capital N here, and the first one can be equal to capital V1 here. So the mathematical equation here we have represented V1 is nothing but the equivalent of the span for the k ranging for phi of 2t minus k here. So accompanying illustration is also, I hope, is sufficient to get you understand what we have exactly done to get more finer versions of the Haar scaling functions here. Now it's to time how getting representation of a signal with the help of these orthogonal functional sets here, or the base elements here. So any signal in this particular functional space can be written as, here we denote it in general, f1 of t here, which is equal to the summation, as in the earlier case also we have done, for k is equal to minus infinity to infinity. So this time it will be ak in multiplication to phi of 2t minus k here. So now you see here, according to this particular equation that you see at the top, we can have the variation into the values of the ak, while the k ranges from minus infinity to this particular infinity here. So varying ak's, we can have generation of the new functions, and a set of all such possible functions will constitute the new functional space that we have denoted by capital V1 on the previous slide here. So a signal that can be represented in this functional space capital V1 is illustrated in the accompanying figure. You see the signal shown with the help of the solid line. Here it is. This is the amplitude level. Next to the this particular interval, we have changes into the amplitude levels like this here. So to have the representation of this particular signal, we have the functional basis from the new functional set. These are phi of 2t, phi of 2t minus 1, phi of 2t minus 2, phi of 2t minus 3. Now you see, as compared to the earlier functional base capital V0, where it was one base that was spanning the time interval 0 to 1 or 1 to 2 this way. So now here we have the functional basis spanning for half of the time duration as compared to the earlier representation. So for 0 to 0 0.5 we have phi of 2t. For 0 0.5 to 1 we have phi of 2t minus 1. For 1 to 1.5 we have phi of 2t minus 2. Then for 1.5 to 2 we have phi of 2t minus 3 here. So this is what the example here, only 4 intervals we have discussed here. So this is what the last interval I have shown here. Now these elements need to have the scaling, so that from the amplitude level 1 we can get to the required amplitude levels as shown with the help of solid line in this graphical illustration here. So this was the example for capital V1 to be the functional space here. So if we try to have more finer Haar scaling function, so for more finer version we will have to get again the variation here. So if we have the representation of the functional space defined by the bases which are phi of 2 square t minus k. 2 square I am making it, so in general you can call phi of 4t minus k. So originally we had the scaling function to be phi of t, then phi of t minus k we have used for v0, phi of 2t minus k we have used for v1. If we make phi of 4t minus k, where 4 is square of 2, so that time we can denote it by capital V2 here. So let us see in this particular expression, v2 is defined here to span with the index variable k or pi of 2 square t minus k here. So in general, we can have the representation of any finer version of the Haar scaling function, that we can label it to in general j. So vj is span for the k ranging for, we have phi of 2 to the power jt minus k here. So this way we have been fulfilling the need that it was to have more finer versions of the Haar scaling function here, and our this attempt is getting us to the concept of nested spaces that we are going to learn in the next video to the same chapter, wavelet transform. Thank you.